So I had a friend in high school who shall remain nameless, who once confessed that when she was a little kid, she couldn't understand why, if you got a burger and a drink at McDonald's or wherever you happened to be eating, why was it that the burger cooled off whereas the soda warmed up? Now, at the time, I kind of gave her some flack for this. But in truth, it's actually kind of a deep question dealing with the thermodynamics of heat transfer. So we're going to talk about that today. Now, what we know is a few things. One of which is when we're talking about heat, we know heat is a form of energy. So just so we're on the same page, let's just state this explicitly. Heat is not the same thing as temperature. Heat is a form of energy. Now, in colloquial speak, we say it's really hot out here. It's really hot. That does mean, in colloquial speak, that means that the temperature's high. But when we say heat, we're going to mean the transfer of energy or the flow of energy. Heat is going to be the flow of thermal energy. So it's got to be moving from one place to another. Transfer of energy from one object to another, from a hot object to a cold object. Now let's go back to our burger and our soft drink over here. Well, we know it looks like there's two objects here, but there's really three. There's three that we're going to be concerned with. There's the burger, which is, assuming it's been prepared correctly, is going to be hotter than room temperature. There's the soft drink, which, if you've got any ice in it, is going to be colder than room temperature. And what's happening is that there's also the air. So the air is at some temperature that's kind of a middle ground. I'll just call that T. So we have the air, the hot burger, and the cold drink, cold soft drink. And there's this rule in physics that says, in thermodynamics, that says, heat flows from hot objects to cold objects, never the other way around. So since the air is an intermediate temperature, it's going to be at a higher temperature than the soft drink. So air is going to deposit heat into the soft drink, but the burger, which is hotter than the air, is going to deposit some heat, some thermal energy into the air. So heat flows out of the burger and into the soft drink. And it's just because of this rule that says that heat flows from hot objects to cold objects, never from cold objects to hot objects. So what we've just discussed is sometimes referred to as the Zeroth Law of thermodynamics. So what the Zeroth Law of thermodynamics says is, let's say I have three systems. I have, or three objects. I have object A, object B, object C. They're all at different temperatures. Maybe object A is very hot, maybe object C is very cold, object B is something in the middle. What the Zeroth Law of thermodynamics says is two things. If I leave these objects alone, eventually they will reach a thermal equilibrium, i.e. they're going to reach the same temperature. They're all going to be the same temperature at the end. In addition to that, we would say that if A is in equilibrium with B, this little symbol is my symbol for equilibrium. It's the two arrows going back and forth. If A is in equilibrium with B, and if B is in equilibrium with C, then it must be true that A is in equilibrium with C. That's our zeroth law. Now, all that really means is that A and B reach the same temperature, B and C reach the same temperature, therefore A and C have to be at the same temperature. It's not, at least on a macroscopic level, it's not that difficult to understand. Microscopically, there is some subtleties with that. It's actually much more deep than I'm letting on right here. But the way it's going to reach equilibrium is that we're going to have heat transferring back and forth. So we'll have some heat flowing from A to B. I'll call that heat flow A to B. We'll also have some heat flowing from B to C. We'll call that heat flow B to C, and that heat is going to keep flowing until such time that this equilibrium condition is reached, where all three systems, A, B, and C, reach the same temperature. So the zeroth law states that multiple objects, when I put them together, if I leave them alone long enough, they'll eventually come to reach thermal equilibrium, where they're all at the same temperature. Now you might ask, well, what is it about what's going on at a microscopic level that forces them all to reach the same temperature? What does that mean? We're going to save that topic for a later time because there's another thermodynamic law I want to get to. And this is the first law of thermodynamics. The first law of thermodynamics we've actually already talked about before because it turns out it's just conservation of energy. In this case, say I have some system. By the way, when a physicist wants to be very general and vague, they just call something a system. So the system can be anything. It could be a gas, maybe it's a magnetic material, maybe it's some biological molecule, maybe DNA, maybe it's a plasma, maybe it's a superconductor. It could be anything. We're going to call it a system because these laws are generally true. They work for any system. It doesn't matter what it is. But I have some system, and it's got to be true that energy is conserved. So if I look at the system and I look at its change in energy, I have to figure out, well, where did that change in energy come from? There's only two ways we can have a change in energy. One way is that I do some work on the system. So I push on it, give it some kinetic energy. I apply some magnetic field to it to give it some magnetism, give it some potential energy. I apply an electric field. I can do a variety of different things to give it energy. But in general, method one is that going to be that I do some work on it. So the energy changes by some amount delta W because I've done some work. The other way the energy can change, let's go green, is if I exchange some heat, which we've called Q. So if I heat it or cool it, I can change the energy. If I do some work on it, I can change the energy. Those are the only two ways that I can exchange energy with a system. Is I either do work on it, or we transfer heat with it. So work, at least for now, we're going to say it's the change in the mechanical energy. Although really, it could be some other type of change. Could be electrical, could be magnetic. So we'll call this, for now, we'll call this mechanical. I'll put that in sarcastic quotes because it could be other things. We'll call that the mechanical change in the energy. Heat, on the other hand, and that would be the thermal change in the energy. So transferring some sort of thermal energy to my system. And when we write this, it becomes pretty clear that we can write changes in the energy very simply. I either have this or I have this. Either have work or heat. So it must be true that the first law can be written mathematically as the change in the energy must be the combination of the work done on the system plus any heat that is added to the system. I'm going to put a big box around this because it's important. It's the only way we can exchange energy with a system. We either do work on it or we heat it up or cool it down. Or we exchange heat with it. So either work or exchange heat. Let's take a simple example of the first law. So say I have some ideal gas. So I've got some ideal gas molecules in a container. The container has some piston, and the piston can move up and down in some cylinder. And what we're going to do is we're going to add some heat. And I think I said let's add, suppose we add 10 joules of heat, so 10 joules of energy, of thermal energy, into my ideal gas. Well, since my container is not fixed to a certain volume, my gas can expand, and as it does so, that piston is going to move up by a certain amount. Just looking at the top of my piston, we will see that it's gone up by a certain distance. It's gone up by this distance right here, which means I've gained this much volume for my gas. In doing so, we have given gravitational potential energy to the piston. So we had to do some work. The work comes in two forms. It comes partly because the piston is getting gravitational potential energy. We're also pushing against the atmosphere, so we're doing work on all of the gas on the outside by compressing the gas in the atmosphere. So when we do this, the work is being done on the outside world, which means we're going to be losing energy from the gas. By moving the piston up, the gas loses energy. And a way to visualize that is if I look at what this molecule is doing, as the piston is rising up, the molecule might come and bounce off that piston. So the molecule comes in, piston is moving up, piston's moving up, molecule bounces off of it. But if the piston is, well, let's take the simple case. Let's say the piston is not moving. The molecule comes in and it bounces off at the same speed. It's a completely elastic collision, no energy is lost. But if I'm moving the piston away from the gas molecule, it doesn't bounce back as fast. Similarly, if the piston is being slammed down, the molecule might come in pretty slow, but then it'll get knocked down by the piston. It'll get more energy. If the piston's moving up, it loses energy, so it bounces back at a slower speed. I'll represent that by a smaller arrow. So we're losing energy by doing work on that piston. So the amount of work that we do has to be some negative number. Let's say we do negative 5 joules of work by lifting that piston up. So we're losing, the gas is losing that much energy. It's gaining this much energy in the form of heat. So we can see, just by energy conservation, very simple. My change in energy is again just the work done on the gas plus the amount of heat added to the gas. Well, technically we're doing work on the atmosphere, which means we're doing negative work on the gas inside the piston. So that work is negative 5 joules. The heat we added, we said that was 10 joules. So it's negative 5 joules plus 10 joules. So the net work, or the net change in the energy of the gas, will be you've added 5 joules. So you put 10 joules of heat in by heating up the gas. You've lost 5 joules of energy by doing work on the atmosphere. You end up with a net gain of 5 joules of energy for your gas.